Alright, so I'm gonna be explaining another important paper with the title LCS graph kernel based on Wasserstein distance in longest common subsequence metric space. This paper in 2021 from Journal of Signal Processing. For graph learning tasks, many existing methods utilize a message passing mechanism where vertex features are updated iteratively by aggregation of neighbor information. This strategy provides an efficient means for graph features extraction, but obtained features after many iterations might contain too much information from other vertices and tend to be similar to each other. This makes their representations less expressive. Learning graphs using path, on the other hand, can be less adversely affected by this problem because it does not involve all vertex neighbors. However, most of them can only compare path with the same length, which might engender information loss. To resolve this difficulty, we propose a new graph kernel based on a longest common subsequence similarity. Moreover, we found that the widely used R-convolution framework is unsuitable for path-based graph kernel because a huge number of comparisons between dissimilar paths might deteriorate graph distance calculations. So we propose a novel metric space by exploiting the proposed LCS space similarity. It means longest common subsequence, and compute a new Wasserstein-based graph distance in this metric space, which emphasizes more the comparison between similar paths. This is an application of optimal transport. But it has some computational problems, so this Wasserstein-Weiss-Lemon graph kernels, which improve the WL kernel by replacing a traditional R convolution framework with an optimal transport scheme. It can improve the optimal transport. So if G1 and G2 are two graphs to be compared, then the R convolution can be written like this. This is the R convolution between two graphs. So K sub D here, K sub D is just a kernel function for substructures in R sub D. So R minus 1 is all x in R that R of G is equal to x. But the traditional aggregation strategies such as pure sum or max or mean are overly simplistic. They might be unable to capture complex features of graph structures. We found that the R convolution framework is unsuitable for path-based strategy because most graphs include a larger number of paths than vertices. Most of these paths are markedly different from each other and are unlikely to be matched. So to overcome this and to compute a similarity metric, we propose this LCS graph kernel using LCS-based similarity and Wasserstein distance. So this is a visual summary of the proposed graph kernel. The shortest paths are serialized as label sequences and are mapped to an LCS space. The Wasserstein distance of two distributions in this space is used as the LCS kernel value. So from graphs we go to path sequences and then this metric LCS metric space. For example, 1, minus 1, 2, minus 2, 1, minus 1, 2. So the goal of longest common subsequence problem is to find a sequence that satisfies these conditions. First, X star is a subsequence of each subsequence in a set of sequences and is longest among all subsequences. So the optimal transport between two histograms is just argmin of T and C. So C of ij is just the cost, the transportation cost between the i's and the j's elements. Now, how do we create these histograms? We define two simplexes of histograms, like this. So in the mass movement problem, PQ are usually regarded as mass vectors of each histogram. So if P is the shortest path, P star of ij represents shortest path from vertex V sub I to V sub j. Because of the difficulty in comparing paths directly, we perform a kind of shortest path serialization before path comparison, for which we serialize these paths as label sequences. So this is the serialized shortest path sequence. And this is path sequence similarity. When we have two path sequences x1 and x2, then we can create the similarity. So the graph comparison of BLCS kernel is just two steps. First, graph representation generation given two undirected connected graphs. The shortest path sets P1 and P2. Through shortest path serialization, we first transform all paths like this. We serialize it. And the way people use shortest paths is just this Dijkstra algorithm, which I've explained in different videos. It's a very classic algorithm, so we can always find the shortest passes of the G1 and G2 respectively. So F serialized denotes the operation of the shortest path serialization. Then step 2 is just Wasserstein distance computation. So given two path sequences x1 and x2, for example, x1 is in x1, x2 is in x2, then the distance is like this. And the theorem says the metric function of LCS metric space is a metric. Here they define this LCS graph distance. And we use the Wasserstein distance, first Wasserstein distance between distributions x1 and x2. It's a very good paper. And then they define this LCS graph kernel. And then it's a fast LCS graph kernel based on adjacent point. So they improve their strategies. So this is the algorithm for computing graph representation in a FAF method. Also computing LCS kernel value, which here we compute ground distance matrix in LCS metric space, and we use the synchron method to compute the optimal transport. This synchron method, we use it in many papers in optimal transport.